Good evening, students. Welcome to the fifth lecture of mass transfer. Good evening, Sunny. What about other people? Only three of you are available right now. Okay. So the yesterday's lecture, did every one of you understood everything? If there is any problem in any concept, just tell me. Okay. Um, just consider it in a simple way that okay. Consider a scenario that right now there are summers, right? It's a hot summer day. The temperature right now is the simple temperature, that is dry bulb temperature, because humidity is very low, and the temperature that will be recorded by the thermometer will be equal to the dry bulb temperature. Okay, now it starts raining. Okay, and it continues to rain for nearly 2 days. Musladhar barish ho rahi hai puri. Okay, what will happen? The amount of water vapor present in atmosphere will be very high. Okay, so the temperature of the air will keep on decreasing. As you might have noticed that after a long rainy day, the temperature of the atmosphere decreases. Okay, so after the interaction with a long amount of water, the temperature of the air is equal to the adiabatic saturation temperature. Okay, got it in the simple terms. Yeah, for air water system, it is equal to the wet bulb temperature. I'll tell you. Today we will discuss the dry bulb temperature as well as the wet bulb temperature. Okay, but for the air and water system, we will get the same value. But for all other systems, like for organic vapors, the wet bulb temperature is higher than the adiabatic saturation temperature. I'll tell that to you on the psychrometric chart. Okay, I'll explain the psychrometric chart to you. Yep, it depends upon time. See, we assumes that a steady state equilibrium condition has been achieved. It means the equilibrium can only be attained at a long time of duration of time. So technically we have assumed that the contacting between water and the air is for a very long time. Okay, and because of that, it is a quite long time period. If the time is less, then the contacting between the two is not so efficient, and the temperature attained will not be equal to the adiabatic saturation temperature, but instead it will be higher than that, but it will be lower than the dry bulb temperature or the normal temperature. Okay, yeah, any other problem? Yes, Sunny. Okay, from lecture 2, what? See, I don't know what kind of case you are talking about. Maybe you are talking about the curve that I made for NA versus DAB or something like that, right? Okay, you are telling how to describe the Knudsen diffusion again. Yeah, okay. Just write down the whole question what you want to ask. What will affect DAB for other two cases? See, if the resistance is too high, then we need to consider the okay. Let's take the consider if the resistance is too low. Yeah, exactly. Okay. See, if this is the mean free path, oh, this is the diameter of the pore. Okay, and now in this case it's going on. Now if lambda is comparable with dp, then we got dk, Knudsen diffusivity, and net diffusivity is equal to 1 upon dAB simple diffusivity plus 1 upon dk, right? Now case number 2, if dp is very large than lambda, it means the pore is not offering any resistance, therefore d effective is equal to dab. Okay, now if diameter of the pore is very less than lambda or less than lambda, okay, then d pore will be very large. Okay, and we need to find out emissivity and tortuosity, and in this case d effective is equal to dab into epsilon upon tau. Okay, because in this case the resistance offered by the path or the pore is very high. Okay, yeah, epsilon is the what, porosity. Yeah, exactly. Tau is what, tortuosity. Okay, so this should be mentioned to you in the case in which it is given. See, if there is a Knudsen diffusion, then Knudsen diffusivity should be given to you. Otherwise, how will you find out the effective diffusivity? Okay, any questions from anyone else? No. Okay, so let's start with the next session, that is our wet bulb temperature and so on. But before starting that, I want to know that how many of you are currently working, or how many of you can only be free in the evening session. I'm just asking if there is a possibility to schedule the classes in the morning session or not, or in the afternoon session. Yeah, you have shift duty. Okay. So you can't the schedule can't be decided for you, right? Because it's too shifting. Okay, you have college. Mm-hmm. Yeah, exactly. I'll go with the majority. I'm just asking if there is a possibility or not. I'm not saying that we will shift it at any point. Okay. Yeah, you also have college. So all of you are free at 6 p.m. only, right? Not before that. Yeah, no problem about that. See, I'm just asking if there is a possibility because when you have a class or you have a job for the whole day, then till the time we reach to the evening time, we usually get tired. Okay, and the things become a little bit of dowsy for us to learn new things. So that's why I was asking whether it is possible for people to attend the class in the morning shift or afternoon shift or not. That was the only reason. Okay, so don't worry about that. Okay, so we'll start our next topic, that is humidification itself, that we were doing in the last class. Now, in the last class, we studied the adiabatic saturation temperature. TS. Okay. Now we will do second, that is dry bulb temperature, TDB. What is a dry bulb temperature? It is the normal temperature recorded by thermometer, okay, under normal conditions. Okay, just simply put the thermometer at a place and calculate the temperature, that is known as the dry bulb temperature. Okay, because you have kept the bulb or the noting bulb of the thermometer to be dry or in the normal state. Okay, so this is known as the dry bulb temperature. Now dew point. So dew point means the dew, that is condensed vapors. It can be anything, yeah. It can be moist or dry air. We just need to have the bulb of the thermometer to be dry. Simple conditions, like and if right now I place a thermometer into the atmosphere, like this is thermometer, we place it into the atmosphere, whether it contains moisture or not, the temperature recorded by it is known as the dry bulb temperature. Okay. Okay. Now dew point. Dew means the condensed vapor. Therefore, and therefore, it is the temperature at which first dew is formed. That is the condensation of vapors just begin. Okay. So this is called as the dew point. After dew point, on further cooling down, the humidity of the air gets decreased. Why? Because because they a little bit amount of or the more amount of it depends ki how much is there, a considerable amount of water gets condensed. So effectively the amount of vapor has decreased into the air. Okay, so if we decrease the temperature below the dew point, the condensation will occur and the humidity of air will decrease. Okay, now the next, wet bulb temperature, TW. Okay, it is the steady state non-equilibrium temperature attained by a small amount of liquid in contact with पानी की bottle with a large amount of air. Okay, which is usually a continuous stream of air. Okay, therefore the temperature and humidity of the air does not get changed in total. Okay, so there are some differences. See, the adiabatic saturation temperature was the temperature measured for the gas, that is air, while the wet bulb temperature is the temperature which is measured for the liquid, that is water. Okay, any question? Any question for anyone? Okay, okay. See, this is the diagram. Let this is the thermometer. This is the shape of thermometer. Okay, now this thermometer is being surrounded by a wick. The measuring knob or the bulb of the thermometer is got by this wick. This is wick. Okay, wick. Air gas in, okay, with a humidity H, temperature T. Gas out with again humidity H and temperature T. Okay, so since we need to contact it with water, so let this is the water which is being added inside it, which is the makeup water. Water at a temperature of TW. Okay, so there will be water embedded inside it. Okay, so the temperature recorded by the thermometer will be equal to the TW. Okay, thermometer. So temperature inside it is also TW, because we are continuously supplying the water, whatever was getting reduced. Okay, so how does this process occurs? What happens that on contacting with a large quantity of air, a fraction of water being supplied gets evaporated by taking heat from the remaining liquid, that is water, thereby cooling down the remaining water, and hence temperature of the wick. Okay, this is how it occurs. There will be a heat transfer between air and water. So during that heat transfer, the heat needs to be supplied. A fraction of water is supply that heat, because since there is a temperature difference and T is obviously greater than TW, it means a heat transfer need to occur. Okay, so this heat transfer will result in the what? Change of the phase of a fraction of water. Okay, so due to which the water will keep on decreasing inside the wick, so we need to supply makeup water inside it. Okay, got it? This is steady state operation and non-equilibrium. Okay, any questions? Yeah, okay. So now let's make the total enthalpy balance. The total enthalpy balance is given by what is the latent heat of evaporation. Latent heat of evaporation is equal to the heat transfer by convection. Okay, that is, this is what? H delta T into T minus TW. So now how will find out the latent heat of evaporation? The latent heat of evaporation is given by what? Using the flux. Flux has the units of kilomole per meter square per hour. So into lambda W, the latent heat of evaporation, which is what, kilojoule per kilogram. So we need to first make it into kilogram. So multiply it with MA, that is molecular mass of what? Molecular mass of A, that is molar mass, that is kilogram per kilomole. Okay, into area. Area has the units of meter square. Okay, so it becomes kilojoule per hour. It is similar to that is used inside the heat transfer. Okay, so the latent heat of evaporation is equal to the heat transfer by convection. Now, equilibrium relationship. Na is equal to ky into y minus yw, or yw minus y. That is amount of water in wet pool is obviously more than simple. Okay, so we'll put inside it, we get, this implies ma a lambda w ky into yw minus y. Now from equilibrium relationship, yesterday I told you that y is equal to h upon ma upon h upon ma plus 1 upon mb. Do you remember it? Right? This is a simple problem that I mentioned it yesterday. So yeah, let's make it curvy. Now if the humidity is low, if humidity is low, then 1 by mb is greater than h upon ma. Therefore y becomes h upon ma upon 1 by mb is equal to h into mb upon ma. Okay, so put inside it, we get a ma lambda w ky into hw mb over ma minus h into mb over ma is equal to ma to ml cancel out. It becomes ky a lambda w mb into hw minus h is equal to ky, oh sorry, h into a t minus tw. A to a gets cancelled out. This implies hw minus h upon t minus tw is equal to h upon mbky into lambda w. So put this value equal to cw. It becomes equal to cw by lambda w, where cw is equal to h upon mb ky known as the psychometric ratio. Psychometric ratio. Okay, so this is the expression similar to that we got yesterday. Okay, or we can write in the simple terms hw minus h upon tw minus t is equal to minus cs upon lambda w. Okay, that is hw minus h upon tw minus t is equal to minus cw upon lambda w. Okay, so this is the characteristic equation, the equation of the psychometric line, also known as the wet bulb line, wet bulb temperature line. Okay, where Cw is equal to h upon mbky known as the psychometric ratio. Okay, significance of PR, what psychometric ratio? Yeah, exactly. It has a lot of significance. See, the wet bulb temperature was given by what? Sorry, adiabatic saturation temperature, right? Yeah, see. So we can take the analogy from any one case and do the problem for the other case also. The other thing is that, see, in real life scenario, usually the wet bulb temperature is attained very easily. So in most of the engineering applications, it is the temperature which is taken into considerations. The adiabatic saturation temperature is attained in a rare case. Okay, so in a way, we need to find out this thing only. Okay, so it has a lot of advantages. Again, while doing the well, I'll explain the psychometric chart to you. There, I'll make the use of both the things. Okay. Okay. Let's make the curve for it. The humidity and the temperature curve inside the wick, that is near the thermometer, and in the ambient air or the atmospheric air, whatever the air we are contacting it with. Okay. So this is the system. Wick was denoted by this color. So wick. Okay. So it contains thermometer, because temperature of the wick is equal to temperature of the thermometer. Okay, and the air was denoted by green. So let's take the dark green. This is the gas. Okay, so temperature that was present over here gets reduced to the wet bulb temperature inside the wick or in the interface. Okay, that is TW. This is T. But overall for the gas it will remain same. So inlet as well as outlet gas, but in the interface and near the wick it will change. Okay, moving out again it will become the same. Now the partial pressure of the air or the water will get changed. That is, here it was PA, Here it will got increased, become it to the partial pressure at the wet bulb conditions. Okay. Similarly, the humidity of the gas will remain same, but it will increase inside the interface and become equal to the HW is equal to HI. PI is equal to PAW. This is simple humidity. Okay. This is how the thing happens inside the system. This is the interface. Got it? See, I told you the temperature and the humidity of the gas will remain same, but inside the wick it will be different, na? While entering inside the wick, the humidity will increase, the temperature will decrease. It will be equal to the wet bulb temperature. Again, when it will leave the leave the wick, the temperature will increase and humidity will again decrease. Okay, this is inlet, gas in. Okay, any questions to anybody? Partial pressure. If the amount of water get increased, won't the pressure exerted by it will also get increased? Isn't the increase in humidity is equal to the increase in moisture content? These are the same things, right? So both the things will happen. See, the total enthalpy Q is given by MA NA into lambda W plus CPA into T minus TW. Initially, when we'll start the operation, that is the calculation of the wet bulb temperature, at that time the sensible heat will also be present. Okay, but after the attainment of steady state, the T will become equal to the TW and this whole term will become equal to the 0. Okay, so as I have mentioned that just a steady state. Okay, so the derivation we have done so far is for the steady state only. If there were not the attainment of steady state, then we will take the consideration of sensible heat also. Okay, also for air water system, TW is equal to TS, that is the wet bulb temperature is equal to the adiabatic saturation temperature. But for all other cases, like for air, organic vapors, TW is greater than TS. Okay, and also TW is generally independent of gas velocity over a wide range of gas flows. Why? Because if the amount of gas that is being contacted is very large, then usually it doesn't matter whether it's moving fast or slow or to a particular range, it won't matter. Okay, but it is if it is too much too low or too high, then only the changes will occur. Now let's get to the next topic, known as the humidity chart. Also known as psychrometric chart. Okay, it is generally the chart describing the variation of humidity with temperature and the change in the corresponding molar volume. But in our studies, we'll consider only the variation of humidity with temperature. Okay, or the exact definition of humidity chart is the it is a chart of properties of air, water, vapor mixture, means the humid air. Okay, at 1 atmosphere absolute pressure. Okay, see, the on increasing or decreasing the pressure, the humidity will also get changed. Like if you increase the pressure of the system, some amount of vapor will get condensed. Similarly, if you decrease the pressure of the system, some amount of liquid present in the or water present into the liquid state will get vaporized into the gaseous state, that is increasing the humidity. Okay, so the humidity chart or the psychrometric chart is studied at constant pressure. Okay, or air water system at ordinary conditions. CS, that is humid heat, specific heat is equal to H upon MB KY. This was equal to what? CW, that is heat for humid heat for battle temperature. This is humid heat for saturation temperature. Okay, this is known as Lewis relation. Okay, and hence in this case the psychrometric line will coincide with adiabatic saturation line. Okay, so for air organic vapor mixture, the dew point is less than obviously aerobic saturation temperature, which is less than wet bulb temperature, which is less than the dry bulb temperature. Okay, for air water mixture, dew point is obviously less than aerobic saturation temperature, which is equal to the wet bulb temperature, which is less than the dry bulb temperature. Okay, but for 100% saturation, if the water is totally saturated, then the dew point is equal to the saturation temperature is equal to the wet bulb temperature, and it is less than dry bulb temperature, because under saturation will become, or in fact it will become equal to the dry bulb temperature, because it won't matter, it cannot be calculated because the bulb won't remain dry. Okay, so even if it is asked that there are some conditions, then it will be greater than these three values. Okay, now let's tell you the psychometric chart. Any questions? Okay, now let's make the psychometric chart. General charts are studied in a different way, and the humidity chart is studied in a different way. It is studied like this. Okay, the humidity will increase there, and the temperature will increase in this direction. Okay, now this is any line for any humidity. Okay, so let the system is at this point. Corresponding to this point, humidity is H1. Okay, so I'm making this curve for any air organic vapor. For air and water, the case will be simpler one. We'll do it again. So this is 100% saturation line. That is percentage humidity is equal to 100%. Here percentage humidity is anything. That is I HS is equal to H. Saturation humidity is equal to this absolute humidity over here. Okay. So this is the percentage saturation line corresponding to wet bulb temperature or wet bulb humidity. Okay, so This is H, this is HS. Then relationship is given by what? This is simple temperature, that is T. This temperature is Ts. It is, since it has a negative slope, because slope is usually calculated from left to right, also right to left. We are calculating it in this direction, so relationship is what? Hs minus h upon Ts minus T is equal to minus Cs upon lambda s. Okay, so the slope of this line is equal to, that is adiabatic saturation line. This is adiabatic saturation line. Okay, the slope is equal to minus Cs upon lambda s. So corresponding to it, now similarly for the wet bulb temperature, Hw minus h upon Tw minus T is equal to minus Cw upon lambda w. Okay, now see, Sw is less than Hs. Hmm? And Tw is greater than Ts. Okay, that is numerator of this case, let this is the numerator n1, this is n2, this is denominator d1 and d2. Okay, so numerator n1 is greater than n2 and denominator d1 is less than d2. Therefore what? This slope is s1, this slope is s2. Therefore slope 1 is greater than s2. But since slope is negative, therefore effective slope, that is negative slope, ne? This is negative slope, this is again negative slope. Therefore effective slope is s2 is greater than s1. Right? I'll explain it by giving you some examples. See, let the first ratio s1 is equal to 3 divided by 4. Okay, so s2 is equal to what? So s1 is negative. Okay, negative, because slope is negative. Again s2 is equal to, we have mentioned that numerator 1 is greater than 2, means 2 will get reduced by 1 and denominator will get increased by 1. Okay, this is equal to what? 3 divided by 4 minus 0.75 is equal to what? 2 divided by 5 minus 0.4. Okay, so which one is greater than? Greater, this one. Okay, when it is taken in the simple way. Okay, so on seeing only the numerical value, 0.75 is greater than 0.4, but effectively the actual is this one is greater. Okay, that is slope 2 is greater than slope 1. Got it? So for this case, let make it over here. This will be psychometric line. Psychometric line. This point will be equal to HW, and this point is equal to wet bulb temperature. Any question? You got the concept, right? How the slope of wet bulb temperature line or the psychrometric line is greater than the slope of adiabatic saturation line, even though the value of SW is less than HS and value of TW is greater than TS. Any problem? Okay, so when this was the point and we started to cool it down, the decrease of temperature, then first TW is achieved and the humidity becomes equal to the SW. Then on further decreasing it down, the TS is achieved and humidity becomes equal to the SW. But after that point, this is the dew point. Okay, so at this point, what will happen? The condensation will occur. So this is known as the dew point, TDP. Okay, on further cooling it down, it will move down the 100% saturation line around here, and see the effective humidity has decreased. Okay, that is H2 is less than H1. Understood the psychrometric chart? Any questions to anybody? See, this chart is a pretty complex one. I have made only a portion of it because this is the only portion that is required for our gate purpose as well as for the common engineering purposes. Okay, so you need to know these concepts which are very important. In fact, these concepts will be useful for you people when you will be doing the process calculations. I mentioned it to you numerically whether it will increase or decrease. See, I have mentioned it, that is, if we consider only the numerical value, 0.75 is greater than 0.4. That is, numerical value was greater than this. But the effective value, that is, on applying of the negative sign, S2 was greater than S1 because it was negative slope. Positive slope means the slope measured in this direction, like this. This is theta. Okay, but right now the theta is calculated in this direction, in the opposite direction. Okay, this is minus theta. This is mathematics that you people studied in 11th 12th, because at the dew point condensation starts. So on further decreasing it down, a fraction of vapors will get condensed, so amount of vapor present inside the air will get reduced, therefore humidity will get reduced. Any other question? No questions? Okay, now for air water system, this line will coincide with this line. Okay, the psychrometric line will become equivalent to that of adiabatic saturation line, and HS will be equal to SW and TS will be equal to TW. Only one line needs to be drawn. There will be no middle line. Okay, this is the only thing that will change. Everything else is the same. Okay, shall we move further? Okay. Before moving further, let's do a question. The GATE 2004 question. Let me open the booklet and just tell you then. It's a simple question. Okay. The question number 98 and 99. Page number 145. That is an air water vapor mixture has a dry bulb temperature of 60 degrees centigrade and a dew point of 40 degrees centigrade. Okay, got the question? Page number 145, question number 98 and 99. GATE 2004 question. Yeah, do this question. चाय की बोलना. Yeah, do the question. No, the answer is D. Try it again. 90th answer is D, not B. D and C are the right answers. Yeah, a pretty simple one, right? One is just put in the formula, everything is given. Anyone else got it? Yeah, it's 0.152. That's right. Yeah, let's move further to the next part, that is drawing. Most probably today or by tomorrow, we will finish the drawing also. Explain the question means what? Shall I do the question on my own? Okay, let me get the question. Yeah, see, the 60 degrees centigrade dry bulb temperature, and the 40 degrees centigrade is the dew point. Okay, right? So at dew point, what will happen? The air becomes saturated, that is, it is about to shed the moisture. So the partial pressure will be equal to the saturation pressure, which is given for this case, which is equal to what? 19.91 kilopascal. Okay, so at this point the pressure is given, partial pressure is equal to 7.3 kilopascal. Now what is left? Put in the simple formula. Total pressure is given as P is equal to 101.3 kilopascal. Simple. Got it? Humidity is equal to what? PA upon P minus PA into MA over MB, right? Is equal to 18 upon 29 into PA is given what? This 7.3 divided by 101.3 minus 7.3. Got the answer as 0.152. Humidity, absolute humidity. So again, in the second question, the question is asked as what? Yeah, the wet bulb temperature. So in the last in itself, what is the wet bulb temperature? This, it will be equal to TDS for air water system, but it will be less than dew point, na? It will be greater than dew point. Sorry, greater than dew point and less than T, because temperature is increasing in this direction. So answer is C. Greater than 40, less than 60. Simple. No, cooling tower is not in syllabus. So 10 minutes tea break for you people. Okay, we'll meet after 10 minutes. Okay. Yeah, we're back. It was a 10 minutes break, but I took only 6 minutes break. No, don't worry. Yeah. Why humidity is calculated at variable temperature, not at the saturation temperature? Absolute humidity is calculated at what? Normal temperature, which is equal to what? The dry bulb temperature, ma'am. The temperature at the saturation point that is being calculated. At that point, the humidity is known as what? Saturation humidity. Okay, at which pressure is equal to saturation pressure or vapor pressure. Got it? Yeah. See, before doing the numericals, before doing anything about the humidification, and also the drawing or any other concept or any other problem, you should first look carefully at the definitions mentioned in the starting of the chapter. Okay, because each and everything that has been mentioned by me in the classroom is important. They have a specific purpose for being told in the class. Okay, so look again for the basics and then try to do the questions. Now we'll start with the drawing. Okay, drawing. When a wet solid is brought into contact with air of low humidity, as is in the case of usually, the solid tends to lose the moisture. Okay, and gets dried up to the value that is in equilibrium with the air. Okay, means the equilibrium value until it attains the equilibrium value, it will keep on decreasing the moisture, it will keep on losing the moisture. So this process is known as the drying. Okay. Now, opposite of drying. What if solid is bone dry? Bone dry means completely dried up, and the air is humid. Then what will happen? The moisture. Okay. See, the power is cut for Sunny, so we will stop for 2 minutes. Resume it again. Okay. 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 So Sunny will not be attending the class, so we'll resume the class. Okay. So what if the solid is bone dry, that is, it doesn't contain any moisture, and it is in contact with the humid air? Then what will happen? The moisture will move from air to dry solid, and this process is known as the opposite of drying, or wetting up of solid. Okay. See, you have seen this phenomena that in simple case, like in summers, when you wash your clothes and put it outside in the atmosphere for drying, the amount of moisture gets reduced from the solid itself. So drying is happening. But what if you place a well dried cloth in the outside atmosphere in winters when it's foggy, or in rainy season? Then your cloth will absorb some moisture from the atmosphere. Okay, so that is called the wetting above solid. This is obviously reverse of drying. Okay, now the definitions, some important definitions. The first, moisture content on dry basis. Okay, let it is denoted by capital X. It is equal to the amount of moisture present, which is in kilogram or gram, that is in mass per unit amount of dry solid. Okay, so in if it is mentioned in 100%, it will written as in percentage, it will equal to 100 into x. Okay, and second, moisture content on wet basis, that this is denoted by small x. It is equal to the amount of moisture present, again in kilogram, upon में amount of moisture plus dry solid. Okay, so on dividing the both sides by the dry solids, denominator and numerator, it will become upon dry solid upon dry solid upon dry solid. This was equal to what? Capital X. This is again equal to capital X plus 1. Therefore, small x is equal to capital X upon x plus 1. Okay. In the similar case, you can interchange them also. That is, or x plus 1 upon x is equal to small 1 by x, or 1 plus 1 by x is equal to 1 by small x. This implies 1 upon capital X is equal to what? 1 upon x minus 1 is equal to, this implies capital X is equal to x upon 1 minus x. Okay, so in this way we can calculate the moisture content. Any problem? So generally, for all our calculations, we will consider the moisture to be on the dry basis. If it is mentioned on the wet basis, either you need to change it or you need to change the other things. That will, that you will understand by using the and doing the problems. Okay, by practicing. Now the equilibrium moisture content. XE. Okay. It is the moisture content of the substance when it is in contact with gas, which is air, for a very long period of time. In such a way that solid and gas are in equilibrium at those conditions. Okay, that is the moisture content when the solid and air, or the surrounding atmospheric air or gas, is both of them are in equilibrium with each other. Okay, so that is the equilibrium moisture content. This is the minimum moisture content, which is, or the yeah, minimum moisture content, which is always retained by the solid, because uh, for removing any more moisture, we will need to change the conditions of atmospheric air, which is usually not done. So if you want to decrease the moisture content from which is lower than equilibrium moisture content, then we need to decrease the humidity of air or increase its temperature, whatever the conditions. We need to change, make some changes into the air surrounding it. Okay. bound moisture. The moisture contained by the substance, by the solid, which exerts partial pressure less than vapor pressure. Okay, so this is known as the bound moisture. And bound moisture means the moisture which has no foundations, means moisture which exerts partial pressure equal to the vapor pressure. Okay, so this is known as the unbound moisture. When the unbounded moisture is present, then the wet solid behaves as if it were a pure liquid only and not a mixture of liquid, that is water, and solid. Okay, because the moisture is exerting a pressure equal to the vapor pressure. It means it acts as if it was a pure liquid only. Okay, free moisture, that is the moisture that can be removed, is known as the free moisture, which is equal to what? The simple moisture minus equilibrium moisture, because actually equilibrium moisture is the minimum amount of moisture content that will remain inside the solid. So apart from that, everything else can be removed. Okay, so this is the moisture that can be removed. Only free moisture can be removed. Now the experiment for doing the drying. See, the drying is done in two phases, in two ways. That is, in batch drying or in a continuous drying. What do we do? That in batch drying, this is again batch and continuous. Okay. So in batch drying, what will you do? We'll take a pan in which we'll keep the moist solid. So this moist solid is in contact with the air that takes away the moisture from it. Okay, this is known as the batch drying. In continuous drying, what do we have? This is a rotary, and this is which is rotating. Okay, in it we supply air and moist solid. So there will be contacting between these two things. They will get contacted, and further, which is air, which is dry initially, it becomes air, which is moist, and solid, which is dry. Okay, this is how it is done. So it can be operated in cross current, counter current, whatever it may be. Okay, we'll consider only one case in our analysis. Okay, So even in this case, for batch drying, first we will measure the weight of the solid initially, then we'll let it dry. After some time, that let t is equal to 1 hour, we'll measure the weight again, weight 1, then t is equal to again 1 hour, weight 2, and so on. So weight will keep on decreasing because amount of moisture will keep on decreasing. So this is how the batch operation is being done. Okay, any question? Look at the definitions. Okay, first look at the definitions. What did you understand from it? That pressure or pressure exerted by the moisture is less than the vapor pressure, that is for the pure water. Okay, I'll explain it in physical terms. Let this is your sheet which you, this is your hanger. Okay, don't mind my drawing, nobody will laugh. Okay, and this is your sheet. See, I'm not so good at trying, but I'll try to make it to the best. Okay, so this is our sheet. Okay, here it is like this, and like this. Right, this is how it is. I think this is how it is. Okay, this is your sheet or bed sheet which is being dried. So initially you just dipped it inside water and then put it here. What will happen? It will contain a lot of water without extracting out the water from it. You just dipped it inside water and then put it on the wire. What will happen? The water will keep on dripping from it. Okay, so at this point the moisture, the pressure, because since water is flowing freely from it, what will happen? The pressure exerted by water is equal to vapor pressure, that is of pure water, because it's occurring, it is going on freely, right? This happens now. Yeah, now let's take the case that it has stopped. That is, now the moisture is contained inside the solid. So there is moisture present inside solid, but it's not dripping out because its concentration has decreased considerably. So this is your moisture which is present inside it. Now, since this moisture is present inside the voids of the cloth, let these are the voids of the cloth, and the moisture is present inside it around here. So the moisture will interact with this wall, this wall, this wall, this wall, and so in order to get it out of here, it need to exert more pressure. That is, the pressure exerted by this PA is less than the pressure that was exerted initially. That is saturation pressure. Okay, because it will exert less pressure because it is bonded. So this is known as the bonded moisture. Okay, initially the moisture that was present is known as the unbonded moisture. Now this moisture is known as the bonded moisture. Okay, got it? Any question? Yeah. Okay. Any questions to anybody else? Okay. Now we will do the best drying. The rate of drying is given by R is equal to minus Ls by A into dx by dt, where Ls is the mass of bone dry solid in kilogram, where A is the surface area available for drying, that is meter square, and dx by dt is what? Rate of change of moisture. Okay, okay, no problem. Okay, so first I'll make the drying rate curves, and then I'll do the derivations. That is time for drying. Now the curves. The first curve is the R versus X curve, and the second one is the X versus T curve. So you must have studied these curves. X versus T curve. And corresponding R versus X curve. Okay, so initially this was the pen which contained solid consisting of liquid inside it. Oh, it's not visible. We'll make it with the different color. So this is liquid inside it. Now on contacting it with the air, let's randomize the air. What will happen? That initially a little amount of moisture will get evaporated. Okay, so initially it will take some time to get restart, like that of your engine. When you start your scooter or motorcycle, it takes a little bit time to kick to start. So this is the initial adjustment. Okay, so initially the rate will be less. Now what will happen? Now whatever the moisture is present inside over here, which was free, that was easily available, will be evaporated by the air. Okay, so the moisture will get evaporated. So whatever was freely available to move on to the surface will also move to the surface and will get evaporated. So the moisture content overall to the surface will remain same because it is moving freely. Okay, now after this point, the whatever was the free moisture, it got, whatever was the unbounded moisture, it got removed. Now only the bounded moisture is present. Now what will happen? Since the bounded will take some restrictions from this surrounding surface, it will not be easy for us to remove that moisture. So it means the amount of moisture available for drying will decrease. That is, it will decrease. Okay, until it reaches a point where moisture content is equal to the equilibrium moisture content. This is known as the critical moisture content. Okay, this is what is X. So this is known as the initial adjustment. So for analysis, we assume that rate was high initially, although it was less. But for our analysis, to make it simple, we assume that it was a high initially, then become constant, then again decreased. Okay, so this is constant rate period. Constant rate period, because R remained constant because moisture was uh, coming to a surface on its own, very without any problem. Okay, now this is the falling rate period. Okay, so on X versus T curve in this region, here this is, let's point, give these points the names. That is, this is A point, this is A dash, this is B, this is C, this is D, this is E. Okay, so on this curve, the curve will be, okay, so this is the initial adjustment which we assumed. So in order to make the curve smooth instead of this curve, so this point is A dash, this is A, this point is point B. So this rate has is increasing over here, sorry, decreasing, and then this is point C, that is nearly constant over here, and then now it decreases. So this is point D, and only this is point E. Okay, so at point E, the moisture content is equal to the Xc. At point C, it is equal to the Xc. Okay, so this is how the drawing occurs in a base drawing curve. Any question? Okay. So what are the unit of R? Kilogram of water per unit area. Okay, the rate at which the water is removed per unit area. The rate means per unit time also. What is the unit of X? That is the moisture content on dry basis. Okay, so this is how the drying rate curve is made for a batch drying. Any problem? Okay, so content is the express to the connection problem. Okay, no problem. See, initially the moisture content was here, so it came up to here. Then now from B point, that is the constant rate period, the x will keep on decreasing at a constant rate. That is, at this point slope is constant. Okay, dx by dt is equal to constant. So it means what is r is direct proportional to dx by dt. These two are constant, therefore r is also constant. So from B to C, this is the constant rate period. Now after that, the slope changes. That is dx by dt will keep on changing at every point. Here it is different, here it is different. Okay, so r will keep on changing. That is, it will keep on decreasing. It is decreasing up to the point A. Okay, got it? Yeah. So I'll explain the theory again. That is, um, first one for the constant rate period. For constant rate period, the surface of the solid is very wet. Okay, and a continuous film of water is present on the drying surface. So this film will act as if there was there were no solid present over there, and it will exert a pressure equal to that of the vapor pressure exerted by a pure water. Okay, therefore the rate of drying in the constant rate period is independent of the solid, whatever its type is. Okay, because the water assumes that there is no solid present over here, so it will act on its own. It is freely, because it's unbounded one. Okay, so evaporation is similar to that in determining the wet bulb temperature. Okay, and for this case, in this case, if radiation and conduction are absent, then the surface temperature is equal to the wet bulb temperature, because it is similar to the case of wet bulb temperature, in which we consider the transfer of V to convection only. Okay, because here again the water was coming freely and it was contacted with a large amount of air. Okay, so it's similar to that of determining the wet bulb temperature. So if the question is asked, then at during which rate period the temperature or the wet bulb temperature is attained, then you will say the constant rate period only. Okay, now in falling rate period, now the interaction of water or the moisture with the solid has taken place. So After the critical point, on moving it further towards point E, what will happen? That water will interact with solid. Now, the movement of the water inside the solid is depending. It depends upon the type of solid that is present. Okay, so the value of critical moisture content depends upon four factor. Type of solid, that is it a porous solid or a non-porous solid? Okay. Then number two, thickness of the material, because as the thickness decreases, value of Xc will also decrease because it will retain small amount of moisture. Number three, the rate of drying. Number four, the resistances to heat transfer and mass transfer within the solid. Okay, so it depends upon lot of factors. Okay, now we will study how the moisture moves inside the porous solid and the non-porous solid. That is how the moisture movement takes place during the falling rate period. A heading: the moisture movement during falling rate period. Okay, number one, in non-porous solids. In this kind of solids, the moisture movement is due to the concentration difference between inside and surface of the solid. Okay, that is diffusion controlled. Similar to the case that we have done in the diffusion inside the solids, that follows Fick's law of diffusion. Okay, so this is in the non-porous solids. So in this case, the curve will be equal to, for this kind of case, the curve will be equal to this. Okay, if we take x is equal to 0, that will be this, or it might come around anywhere. Okay, this is r, this is x. It will be a curve because the mass transfer, as we have seen in interface, it becomes a curve. Okay, instead of a straight line, it becomes a curve because a single phase solution of moisture and solid is present. Okay, in this case we assume that since it's the diffusion controlled only, so in order to make the analysis easy for us, we assume that it is a single phase solution and it exists, it acts as if that whole solution was a single entity. Okay, example, in soaps, paste, glue, etc. Okay, now since it depends on the concentration difference, that this is the solid, here concentration is CAI and here it is CAS. So we'll keep on removing moisture from surface. Okay, so which will result, since it is removing from here and the moisture is moving from inside to the surface, so in a way CAS was remaining constant because it was being replaced by the moisture moving from inside, but CAI will keep on decreasing. Therefore the difference between, that is CAI minus CAS, it will keep on decreasing. Therefore driving force keep on decreasing as shown in this curve. Okay, so driving force is decreasing, so we get a curve. Okay, for this case the whole, the mass transfer operation is explained by unsteady state mass transfer, that is curly x by curly t is equal to the DAB or DAB of the liquid into curly square x upon curly z square, where z is the distance. Okay, now similarly, so if now consider the case if the air contains moisture, like if you are drying your clothes in winters or during rainy season, then what will happen, the clothes get dried up very late. Okay, why? Because the moisture content, that is CAS, will increases if the air has high humidity. CAS will increase, but CAI was constant, therefore CAI minus CAS, it will decrease. Therefore driving force decreases. Therefore it takes more amount of time to dry the solid to the same final moisture content. Okay, because the drying force is decreased, that is mass transfer will decrease. Okay, this is how it occurs. Any questions? Any question from anybody? So this is a steady state equation, so which is not in our curriculum, so we will not be doing it. So see, at the end of mass transfer, when we'll do all the operations, then I'll tell you how to solve it also. Don't worry about it. How can we solve a simple steady state problem? Okay, I'll tell that to you, but it's not mentioned in the engineering curriculum and in the gate curriculum, so we'll not be doing it right now. Okay, any other question? Okay. If there is no question, then we'll move on to the second case. That is, if the solid is porous. I have a lot of water bottles around me. That doesn't matter. But it's good that if you have the same water bottle. So in a way, we are water bottle buddies. Okay. Yeah. So to teach for continuously for 3 hours, it's a little difficult task, right? Because you have to speak continuously for 3 hours. Don't worry, it becomes habit eventually. Now for the porous solids. See, I don't have any problem in giving you the rest for 5 minutes. You should just ask with each other whether or not you want the 5 minutes break. Okay. See, we live in a democratic nation, so whatever the democracy says, okay, don't worry. From tomorrow itself, after every 50 minutes, I'll give you a rest for 10 minutes. Okay, like we start at 6:15, so I'll give you 10 minutes break at 7:05, then 10 minutes break at 7:55. Okay. No, no, I'm not the best. The best is yet to come. Okay, so let's do the second question, second problem, that is the porous solids. Huh. In porous solids, the movement is due to the capillary movement. The capillary action of the moisture that is moving from inside to the outside. It will result in the motion. Okay. So the rate curve in this case will be equal to this. Then decreases further. Okay. This is the point C. Let this is point one, or this is point one, this is point two, this is point three. These points will make it easy. Okay. So the movement, or this, the motion in the porous solid is very much similar to the motion of oil inside wick. How many of you have seen oil lamp or diya, right? That we used in the Pavli, or simple case. Yeah, right. What happens that in this case, I'll make a drawing, but nobody will laugh because my drawing is not so good. Let's make a diya. Okay. um, this is too shallow, don't worry. Okay. So this is its wick around here. Okay. I'll make it again. It's a little difficult to make these drawings. Okay. This is the top surface, this is the inside of it. Now it contains wick. Let this is the wick which is present over here. Cool, right? This is the wick. Now we filled it with the oil. Let's take oil of green color. What will happen? This oil will seep inside this wick and move inside it and reach to the surface. Now, when we ignite it, flame is generated over here. Okay, this is the color of flame. Cool, right? So this is our flame. It is of blue or yellowish color. It contains a little bit of yellow and a little bit of blue also. So this is our flame. Okay, so flame is generated, but what is the main thing that here the moisture or the oil which was present is continuously burned. So here we have a drying force which is equal to Cs, because amount of oil that is present at this point which is needed for the burning of flame, it is constant, but from inside the liquid needs to move, otherwise it will deplete and the flame will get exhausted. Okay, it will be extinguished. Okay, so the movement is due to the capillary action. I won't mention tell you the capillary action in detail because that is a fluid mechanics problem, or we can say MO problem. Okay, not mass transfer problem. So when we will doing mass transfer MO or fluid mechanics, then I'll mention the capillary action. Okay, so due to capillary action, the liquid moves to the surface. This is the same thing that happens inside it. Okay, in this 1 to 2 region, the movement of the moisture due to the capillary action. Okay, but in this case the meniscus will keep on decreasing because the water will keep on decreasing and inside driving force has is decreasing. Okay, but uh, the region 2 to 3 can have two special cases. The case 1, if the solid is very much porous. Now, if the solid is very much porous, then what will happen? Then this 2 3 region will be similar to the 1 2 region, and it will be a straight line like this. Okay, but if it is moderately porous or even less porous, then region 2 to 3 is diffusion controlled. Okay, so it will be influenced in a similar way like that of a non-porous solid. Any questions? Okay, I got an idea. You know, what is the maximum time for which an average human can sustain its concentration of the mind? That is, the mind can work efficiently. What is the maximum duration? It's 45 minutes. Somebody will say that it's only 2 minutes. Okay. Uh, yeah, it is around 45 minutes. So I'll give you a break after 45 minutes for 5 to 10 minutes. Get fresh, get refreshed with your mind, and then we will start again. That, and by that time, so giving that time will only increase your efficiency, which is bad, which is very good for you. Okay. Now we will do the derivation for the calculation of drying time. calculation of drying time t. Okay. Number one, constant rate period. It is simple one because r is constant, so it won't vary with x. So it's linear. So r is equal to minus ls by a into dx by dt. So on rearranging, dt is equal to minus ls upon ar into dx. See, I have a little attenuation. Someone is playing DJ outside my office, so you might be listening to some music. So don't get distracted and listen to only my voice. Okay. Now integrating both sides within the proper limits. Okay, so it will become t is equal to minus ls upon ar x2 minus x1 is equal to minus upon ar into x1 minus x2 because x1 is greater than x2. Initially there was more moisture. After drying, moisture will get reduced. Okay, so this is the expression for time of drying in a constant rate period. Simple. Now in this case, R is equal to RC because the rate remains constant until it reaches the critical point. Since the critical point is the point which is used in the following rate period also, so we will consider R is equal to RC. Therefore, T is equal to Ls upon ARC into x1 minus x2. This is the time needed to dry out a solid in a constant drying rate period. Okay. Any question? Okay. Now, what are the factors affecting constant rate period? Obviously, if we increase the velocity, the heat transfer coefficient will increase. That is, H will increase. So overall heat transfer will increase. Therefore, time will increase. Okay. So in absence of conduction and radiation, drying rate direct proportional to the heat transfer coefficient H. Now H is the Nusselt number relationship. H is calculated from Nusselt number, which is direct proportional to Reynolds number. Okay. So on increasing the velocity, the value of RC will increase. So there are some empirical relations which are given that when air flows parallel to surface, H is equal to 0.0204 0 to 0.8. Okay. Similarly, when air flows perpendicular to surface, H is equal to 1.17 into g raised to the power 0.37. Okay, so on increasing the where g is equal to superficial mass velocity. Mass velocity is equal to rho into v. V is velocity. Okay. Huh. Now similarly, second, it depends upon the gas humidity and the gas temperature. That is Rc2 upon Rc1 is equal to Hw2 minus H2 Hw1 minus H1 is equal to T minus Tw2 upon T minus Tw1, because rate is what? It is similar to Na bar, and Na was equal to what? A into, oh, Na was equal to Ky into Y minus Yw minus Y. So Y was equal to what? Mv over Ma into Hw. So in a way, Na bar, this is equal to what? Na bar upon area. All these relationship are already done. Okay, so Na bar, that is over Rw, is direct proportional to Hw minus H. So we have mentioned this. And from psychometric chart, we have shown that this is this. Okay, so this is how it varies with gas humidity and gas temperature. Now, third, thickness of the solid. Right, where L is thickness or characteristic length. So it, in a way, H varies with thickness. But the case, if conduction and radiation are not present, then Rc is unaffected by thickness, because L will change for both Re and Nusselt number. It will cancel out. However, time will increase. Why? Because it will retain more moisture. Moisture. That is, Xc will increase, and drying rate period of decreasing rate will be achieved very early. Okay, see, the constant rate period drying is achieved very easily when you can do this experiment today also. Just right now, after the exam, the class is over, and go to your room or whatever you are, wherever you are living, at your house, in a hostel, whatever it is. Go there and make a piece of cloth. Let it be your hanky or whatever it may be. Okay, XYZ, any piece of cloth. Put it inside water and then put it out for drying. So initially it contains totally unbounded moisture, so it will keep on drying at a constant drying rate period. You will observe that it will uh, lose the moisture very easily initially. Then after eventually after some time, the drying rate will decrease, and the rate on the time required for drying will increase. Okay, because as soon as the critical moisture content is achieved, the rate of drying decreases and the time for drying increases. Okay, so it will again. So for us it's favorable that the critical moisture content is attained very much near to the equilibrium moisture content, because then we will have a very less falling rate period. Okay, now we will calculate the time for drying in the falling rate period. Any questions? Because this is the last division which we will do today. Okay, okay, so from last derivation we got r is equal to minus ls by a into dx by dt. Okay, let me put it. So from here this implies t is equal to minus ls upon a into integration of dx upon r. Okay, so this is the general formula if x1 to x2 it is decreased. Now case 1, r is a linear function of x. Then what will happen? R is equal to ax plus b. No, this is the curve. R x xc. This is point 1. This is point 2. Okay, x1 and x2 are present over here and here. So what is a? Dr is equal to a into dx, but a is equal to what? R1 minus R2 upon x1 minus x2. How did we get it? Put the value of r is equal to x plus b from point 1. We get r1 is equal to a into x1 plus b. Similarly, r2 is equal to a into x2 plus b. This implies r1 minus r2 is equal to a into x1 minus x2. This implies a is equal to r1 minus r2 upon x1 minus x2. Yeah, slope. Okay. I mentioned it mathematically because sometimes people don't, you might not be able to understand it right now. See, it's not that you don't know the concept, is that whether or not you are able to use that concept at that point of time or not. Okay. Now, so dr is equal to a into dx. Okay, or dx is equal to dr over a. So put inside it, we get t is equal to minus ls by a into integration from r1 to r2 dr upon a into r. So it will become minus ls upon a into ln of r2 by r1, multiplying it inside ls upon a ln of r1 by r2. Okay, so this is another formula. So it will become what? A is again this. So we can put t is equal to ls by a into a is given as r1 minus r2. So it x1 minus x2 upon r1 minus r2, because a is at the downside, r1 by r2. So this is the general formula for time in the falling rate period when r is a linear function of x. Now the special case. If this function, this falling rate period falls starts from the origin. Case 2. The falling rate period starts or terminates. You can say anything. If you think that it starts from here, then it terminates at here. If you think that it starts from here, then it will start from here. Terminates at origin. And what will happen? R is equal to Ax. Okay. So this is value 0. This is value of xc. So A will be equal to what? Rc minus 0 upon xc minus 0 is equal to Rc upon xc, because the slope is from 0 to Rc comma xc. Sorry, is xc comma Rc point. Slope is equal to, again, Rc upon xc, right? So this is the expression. So the expression can be this. So R1 is replaced by R2, Rc, and point 2 is point 2. So for at any point, t is equal to minus Ls upon A, where A is given by Rc upon Xc, that is Xc upon Rc into ln of Rc upon R2. Okay, this is the most commonly used formula. Any question? Yeah. So this is how it is done. Okay. So for any point, so this is equal to r by x. For any point, let this is point 2, this is r2 by x2. So or r can be calculated as x into rc upon xc. So this is how the rate is calculated at any point in the falling rate period. Okay, this is how it is done. So this is the falling rate period, time period. So that's it for the falling rate period for the batch drying. So tomorrow I'll tell you the case of continuous drying, and then we will do some questions. So by the time you can try the questions on your own, I'm pretty sure that you will be able to do all the questions. So if you'll try the questions at home today, then we will start the exhaustion stripping tomorrow. Okay. So start from the basic, put the values, rearrange it, and finally get the expression. Okay. The simple case. Okay. Any questions from anyone? Or shall we do the continuous drawing also? I don't have any problem in teaching you the continuous drawing today also, but that is a little bit of tricky part. Okay, it requires nearly half an hour of time to explain it completely. So that's why, and apart from that, it is the best drawing that is asked usually. Yeah, class will be always over by 9 p.m. You need not worry about that. Okay. Any questions from anyone? Yeah, we'll do the continuous drawing tomorrow. Okay, so good night to all of you. uh, Revise all the concepts that I have taught you today. Okay.